So this is the second in a series of quickfire videos designed to help you pass your City and Guilds 0610 exams. So we're going to start today by imagining that we have a cylinder and that cylinder is filled with fluid. We then place a particle into this cylinder and we ask ourselves, how quickly will that particle fall to the bottom of the cylinder? That is to say, how quickly will that particle fall through that fluid to the bottom of the cylinder? Now, this question may seem a bit abstract when you first learn about it, but actually in chemical engineering, this is a very important question because it helps us to design things like mixers, and it also helps us to design things like sedimentation tanks. Now, to answer this question, we're fortunate enough that we have Stokes' equation. So Stokes' equation tells us the velocity, that is how fast that particle is going to fall through the liquid. A minute now to pause the video and write down the equation. Now this equation, Stokes' equation, tells us the terminal velocity of a particle, or to say it another way, the maximum speed that the particle will fall through our fluid to the bottom of our cylinder. Let's look at the terms in this equation. Take a minute now to write these down. We can see on the top of our equation we have r, which is the radius of the particles. We also have this part in the brackets that represents the difference in densities between the particles and the fluid. So that part in the brackets is telling us how much more dense our particles are than the fluid they're in. And lastly we have g, which is acceleration due to gravity. Now g on Earth will always be fixed, therefore the equation is telling us that we'll get a bigger velocity, i.e. the particle will fall through the fluid faster if the particles are bigger, i.e. have a higher radius, or if the particles are significantly more dense than the fluid. Looking at the bottom part of the equation, we have viscosity. And it's important to note that viscosity is times by 9 here. So viscosity has a huge effect on slowing the particles down. They fall through the fluid less quickly if the viscosity is higher. And this makes sense. So to think of it another way, if we have a thicker, more gloopy fluid, so if we had, say, treacle instead of water, it would be harder for a grain of sand to fall to the bottom of a jug of treacle than it would to a jug of water. So viscosity has a huge effect on how quickly the particle can fall through the fluid to the bottom of the cylinder. The last part that we need to note on this slide, and a really important part I'm going to circle now, is acceleration due to gravity. Now City and Guilds may try to trip you up with this part. This number is often left out, as we will see, on exam questions. So it's worth making a note that acceleration due to gravity is 9.81 meters per second squared. Now to pause the video and read the question. Now, as we said on the previous slide, they've left out acceleration due to gravity. So before we can answer the question, we must recall that acceleration due to gravity is 9.81 meters per second squared. We also have another potential slipping point here because we have not been given the particle radius in its SI unit of meters. So therefore we need to convert the particle radius into meters. I've put a handy clue for doing this on the slide. However, I strongly suggest that you practice unit conversions for your 0610 exam. Plugging the numbers into the equation, we have 2 times 0.000045 meters squared. So 2 times the radius squared. We then times that by the difference in density between the particles and the liquid. So 1255 is the density of our particles and 997 is the density of our liquid. And we then times that by our acceleration due to gravity. On the bottom part of our equation, we then have 9 times the viscosity of the fluid, which is 1.005 times 10 to the minus 3 Pascal seconds. Plugging all of these numbers into the equation, We should get an answer, if we've done this correctly, of 1.113 times 10 to the minus 3 meters per second as the terminal velocity of particles that would fall through this liquid. This is the same as saying approximately 0.113 centimeters per second, or that is to say, therefore, about a centimeter every 10 seconds.